Okay, this video discusses an application of a derivative that actually helps you to find limits. So if we revisit limits for just a minute, we're going to use what's called L'Hopital's rule. And L'Hopital's rule states that if you are evaluating a limit, and that limit is a rational function f over g, and f and g are both differentiable, then if you evaluate this limit and you get 0 over 0 or infinity over infinity, so that's what you're looking for. If I end up with one of those two indeterminate forms, 0 over 0, infinity over infinity, then what I can do is I can actually take the derivative of the two functions separately. So I'm not going to use the quotient rule here. I'm just going to take the derivative of the top and the derivative of the bottom, and I'm going to reevaluate the limit. And whatever the answer to that would be is the same as what the answer to my original limit would be. Okay, so this helps in the case of when I go to evaluate a limit, what I try to use is direct substitution, right? And if we get an indeterminate form, previously when evaluating limits, all we looked at was okay, we have to factor, or we have to multiply by a conjugate, something of that form. Well, now we can use L'Hopital's rule to help us with this. So on this first one, if I were to plug in 1, right? If I were to plug in 1, I would get 1 minus 1 over 1 minus 1, which is 0 over 0. So because we get that indeterminate form, what L'Hopital's rule says that we can do is we can reevaluate the limit as x approaches 1, and all I need to do now is take the derivative of the top, which would be 2x minus 1, and the derivative of the bottom, which would be 2x, and then I can reevaluate this limit by direct substitution. And if I plug in 1, I get 2 times 1 minus 1, which would be 1, over 2 times 1, which would be 2, and so my answer to my limit would be 1/2. And that is the nice thing about L'Hopital's rule, is it allows us to evaluate limits relatively quickly. So number 2, if I were to plug in 0, the sign of 0 is 0 over 0. I can use L'Hopital's rule. So the limit as x approaches 0 of the derivative of sine is cosine, and the derivative of x is 1. So we get the cosine of 0 divided by 1, which would be 1 over 1. So the answer to our limit is 1. Limit as x approaches 1, natural log of 1 is 0, and the natural and 1 minus 1 on bottom is 0 again. So I can use L'Hopital's rule, get 0 over 0. So I get the limit as x approaches 1. The derivative of the natural log of x is 1 over x. And on bottom, the derivative of x minus 1 is just going to be 1. Now if I plug in 1, I get 1 divided by 1 on top, which is 1. On bottom, I get 1. So the answer to my limit is 1. Okay, if we go to infinity, well, e to the infinity power over infinity squared, that's still going to be an infinite answer divided by an infinite answer, right? E to the infinity is going to be something really large. So is infinity squared. So I get infinity over infinity, which is again an indeterminate form. So I can do the limit as x approaches infinity. I can do the derivative of these. Well, that's still going to be e to the x on top. The bottom is now 2x. If I plug in infinity, I get e to the infinity, which again is infinity. And on bottom, I get 2 times infinity, which again is infinity. So I have the indeterminate form again. So I can do another application of L'Hopital's rule. The limit as x approaches infinity. The derivative of the top is e to the x. The derivative of the bottom, derivative of 2x, is now just 2. And now I get e to the infinity divided by 2, which means we're going to have infinity divided by 2, which is still going to be infinity. Now, that's not infinity over infinity, right? So that's my answer. My answer, my limit is infinity. It's different than this infinity divided by infinity there. So that one took 2 applications of L'Hopital's rule, but as long as I keep getting indeterminate forms, I can keep applying L'Hopital's rule. for this last example, if I plug in 0, the sine of 0 minus 0 over 0 cubed, that's going to give us 0 over 0. So I'm going to use L'Hopital's rule here. Limit as x approaches 0. The derivative of the top, the derivative of sine is cosine, so I have cosine of x minus the derivative of x is 1, and on bottom 3x squared. Well, if I plug in 0 there, the cosine of 0 is 1, so on top I get 1 minus 1, and on bottom I get 0. So again I get 0 over 0, so I'm going to use L'Hopital's rule again. Limit as x approaches 0. The derivative of cosine x is the negative sine x. The 1 goes away. Derivative of the bottom, 6x. If I plug in 0, the sine of 0 is 0, so again I'm going to get 0 on top, and on bottom I'm going to get 0. So I'm going to use L'Hopital's rule again. The limit as x approaches 0. The derivative of negative sine x is negative cosine x. The derivative of 6x is 6. Now I can evaluate the limit. If I plug in 0, negative cosine of 0 is 1, so it's going to give me negative 1 over 6, and that is my answer, negative 1/6. This is an example of a problem that would be very difficult to solve using any other method. If you tried using factoring or conjugates or all those methods that we had before, this is a problem. A lot of the problems that we have here are ones that would be difficult to try to use some algebraic method to help you solve those. So L'Hopital's rule helps you evaluate more challenging limits, but also easier limits that we could have used factoring on to help us get away from that algebraic model. Okay, so if you know derivatives, you can use L'Hopital's rule to apply it to limits.